In this video, we're going to see an integral that may not look immediately like a substitution integral, but substitutions are something we can try if nothing else seems like it's going to work. Let's consider this integral here to start with and look at it as something that guessing and checking doesn't seem to help. I can't imagine what would work here, like maybe ln of absolute value of x root plus 1. That's not going to work though, because the chain rule is going to create some horrible offshoots. So yeah, we need to do something, but it's not clear what we should do. Well, what we can try is a substitution. Now this does have an inside function. In the denominator, which is inside a radical or inside a power of -1, we do have something. So it might be worth just trying w equals square root of x plus 1 just to see what happens. If we do that, we just follow the process, we turn the crank, the derivative would be 1/2 1 over root x plus 0, or isolating for dx, we'd bring the 2 root x up, and that would be our arrangement for the dx term. That means that our integral could be rewritten as 1 over, the denominator altogether was called w, and this looks really good until we go and mess it up with the dx. The dx is 2 root x dw. This is a problem because we have a mix of w's and x's, and that is a big no-no. We cannot take any further steps if we're going to have this cross-contamination of x's and w's. So now what? Well, that's the problem. W's and x's mixed. Could I get rid of this x somehow? It didn't get canceled sort of for free like other substitutions have, but maybe I could write it in terms of w in another way. Then if we're scanning through the page, we're like, hello, root of x is right here. In fact, root of x could be rewritten as w minus 1, right? Just bring this 1 over, it becomes negative. And hey, problem solved. 1 over w times 2, and that root of x can be rewritten in terms of w's. Now, is that any better? It doesn't look like it at first glance, but it actually is. We've got w minus 1 over w. And if you think about how fractions work, having complicated denominators is a real mess. Complicated numerators, though, are fine. We can split numerators into separate fractions all over the common denominator. So we're going to do that here. W over w, that's one term, minus 1 over w. Well, that is not bad at all, because that's 2 times just 1 minus 1 over w. This is now simpler, and it is all w's. That sets us up perfectly to actually evaluate the integral, which we'll do on the next page. So the integral we started with, we got to rewrite in this form by choosing w equals square root of x plus 1. Now we can integrate. We just have to be a bit careful about what variable we're using. W is our integral variable, so when we integrate the 1, we get a w. And then the integral of 1 over w is ln of w. What a treat tonight. That's our integral. Don't forget to add the plus c because it's not a definite integral. We are looking for a function or a family of functions. And then last but not least, we go back to x's. W was square root of x plus 1 outside the square root, minus ln absolute value of square root of x plus 1. And that, with a plus c at the end, would be a perfectly valid integral of the function we were given to start with. Again, noticing the pattern, there was not here an obvious inside and derivative outside that has marked some of our other substitution integrals, but we just tried something And when we ended up with an extra x that we needed to somehow remove, we went back to our w definition to see if we could rearrange it somehow to get rid of that root x. In fact, that was possible, and that allowed us to turn everything into w's and then complete the integration steps. Again, the hallmark of learning these skills is trying things out, being careful about the steps, but most importantly, checking as you go whether what you've done has worked, hasn't worked, and if you can take that extra step, trying to figure out why it has worked or has not worked.